In order to understand anything about the canyonlands, you have to understand something about rocks. So we want to have a short discussion about petrology, the study of rocks. One of the problems and one of the mistakes that people make in interpreting the canyons, and sometimes you hear various religious theories connected with how the canyons were produced, happens because people don't understand the nature of rocks. So much of what I'm going to do here is probably something you're already familiar with to some extent or another, but we need to establish a couple of things and help answer a few questions. What produced the Grand Canyon? Is it possible, for example, that it was produced by the flood of Noah? Or are there perhaps some reasons why that couldn't be a rational explanation in terms of the rocks themselves? Now on the table here, to start out with, I have three basic kinds of rocks. Volcanic rocks. Now you have to understand in every one of these cases there's lots of examples, and we'll talk about each of these groups individually, but this is a good example of what Mount St. Helens is about. This is a rock that was extruded from a volcano. And as you look at it, you can see it has gas holes. You can see that it looks very much like a cinder. It has flowed. It has picked up material as it flowed. So that's a volcanic rock, Mount St. Helens. Good example. There are other kinds of rocks. This particular rock is called pyroclastic. Pyro, fire, clastic, basically talking about a piece or something that has a particle nature to it. Now, if the material was not thrown out of the volcano very quickly, which is what happened to this one, then the gas holes wouldn't be there. This thing was bubbling and frothing, and gases were flowing out of it as it emitted from the volcano. But sometimes lava moves along the surface very slowly, and so you get a very different type of material. I'll show you an example of that here in just a minute. Sometimes the lava doesn't even get to the surface. Sometimes it's much deeper. So it cools fairly quickly, not fast enough for any significant crystals to form of material, but nonetheless, no gas holes. And basalt, which you are probably familiar with, is a good example of that. Volcanic rocks are a group of their own. If we understand the history of the earth properly, either from a biblical perspective or from a scientific perspective, when the earth was first created, it was without form and void. Volcanic materials dominated the surface of the earth as well as the interior. Now our second rock here is a sedimentary rock. And this particular sedimentary rock came from Frankfort, Kentucky. I'm going to take you on a little tour of my rock garden here to show you how I know that type of thing. But this is a material that is made of sediment that is cemented together. No volcanic connections directly here at all. And in fact, as you can see, there are fossils. These particular fossils are called brachiopods. Most of these are a specimen called Eospirifer. That's the name, just like Cocker Spaniel or something like that. But this is a rock produced under sedimentary conditions, flowing water, laying down material, or in a quiet ocean, material being precipitated together, and anything living in the environment at that time would be preserved with it. So that's a sedimentary rock. The third type of rock is called a metamorphic rock. The metamorphic rock is one of these other two that has been compressed and heated. Now, this particular one is connected with a volcanic rock. And let me show that to you. We'll move some things around here. This is a piece of a material called diorite. Now, diorite is a material that never got to the surface. It was nowhere near this. It was deep down in the ground. So instead of being pyroclastic, this one is intrusive, or plutonic, sometimes people call it. It is deep down in the earth, and it cooled very, 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 very slowly. So you find diorite in places not where the volcano is, but deep down in the ground, some distance from the volcano. What would happen if I put massive amounts of pressure on this, like this, and perhaps heat it a little bit? What would happen to the rock? Well, what happens is that the darker materials join together, making bands, and the lighter materials join together, making bands, and we have a rock which is called gneiss, G-N-E-I-S-S. Gneiss is a metamorphic rock. It is this stuff compressed and heated, and the direction of pressure came like so. Now, could this material become a metamorphic rock? The answer is yes. If that happened, it would be marble. What do you think would happen to the fossils if I were to subject this rock to massive amounts of pressure and heat? Well, they would be destroyed, wouldn't they? Nothing of a natural specimen could possibly survive that. So all metamorphic rocks are either sedimentary rocks which have been changed or volcanic rocks that have been changed. And it's important to understand that every rock you can think of can have a metamorphic equivalent. Shale turns into slate. Gravel, which forms a rock called conglomerate, turns into metaconglomerate. You can even take metamorphic rocks and change them into other metamorphic rocks. If I took that piece of gneiss and continued to squeeze it and to heat it, it would turn into a much finer grain of material. And if there is mica in the rock, it might tend to line out, and we have a name for that. It's called a schist, S-C-H-I-S-T. Now, I don't want to bother you with all the names of these different rocks, but I want you to understand the different processes because this has a major impact for how we understand the canyon. All right, let's talk about volcanic rocks for a minute and how they impact our study of the canyon. On the table I have a group of volcanic rocks. We already talked about one here that is a pyroclastic rock. This is a kind of rock you would see in St. Helens. Most of the area surrounding St. Helens is made of this. This is the stuff that flew out and went down. Of course, it was red hot at the time, knocking down trees and wiping out Henry Truman's place and so forth. This is another example of the same type of pyroclastic rock, but I wanted you to see it to notice the flow. And this one does not have as many gas holes as this one did because this is more of a lava flow. It's a little bit further from the volcano, less violence, less material being kicked out. And here's a piece that actually came from Devil's Tower in Wyoming. But you'll notice it has what's called columnar jointing. Now, this doesn't have any gas holes. So this is a rock that was not exposed to rapid cooling. By the time this rock solidified, there were no more gases bubbling in the rock, so it's not pyroclastic in the sense of having frothing and bubbling as the gases are coming out of it. And it cooled quickly enough that there are no large crystals in it. Now, if you look at the rocks on the back side of the table, you'll notice that we're dealing with rocks that do have crystals in them. And I'm sure you recognize this. This is a piece of granite, good old-fashioned granite. What you may not understand about granite is that granite is a rock that is really the parent of much of the other stuff that we see in nature. Because this is made up of material that crystallized deep inside the earth. When we drill wells anywhere on the earth, just about, except in the oceans, but anywhere on a continent, we eventually run into granite. In North America, the Canadian Shield is mostly made out of granite, but the rock is deep down inside. There are places where the rock has been pushed to the surface, and we have names to describe those types of uplifts, and so granite is frequently exposed. Now, as you look at this piece of granite, you'll notice it has lots of crystals in it. It cooled very slowly, and so crystals grew in the rock. And geologists, as they look at this, recognize certain crystals. The pink material in this rock is something called orthoclase. Now, what's interesting about orthoclase is that when orthoclase weathers out of the granite, you leave it outside for a long time, it turns into clay. So much of the clay that we see in the natural world is a byproduct of granite. Now, some intrusive rocks, like the piece of diorite that we looked at, does not have any orthoclase in it. And so the difference between this rock and the granite is really the presence of orthoclase. You also notice in both this rock and in the granite, there are some black pieces. Some of it's little shiny crystals. That's called biotite. It's like mica, a kind of mica. Hornblende is the other. That's a mineral that's made up of iron and manganese and so forth. And the white stuff in both of these rocks, which is the dominant material of the rock, is quartz. Now what happens if you leave this stuff outside for a long, long time? Like here's a piece that's been left out for a long time. Most of the pink is gone, isn't it? It still has the black and the quartz and so forth and so on. And here's a piece that's been out even longer. And look, it's coming apart. And what's left when all the pink stuff is gone and all the black stuff is gone? Good old Michigan sand. So when we see sand, quartz sand, in a huge number of cases, the sand is what's left over from the weathering and erosion of intrusive volcanic rocks. Sand is the ultimate product of the weathering and erosion process. So when we see a sandstone, and the sandstone is made up of the kind of quartz sand that we're talking about, what's the genesis of that sandstone? Well, usually there's going to be a granitic mountain range somewhere nearby. Now those are all volcanic rocks, but remember that clay comes from granite, that sand is the last thing to take place when granite is eroded. In the Grand Canyon, how much granite do we have? Very, very little. There's a granite called the Zoroaster granite at the very bottom of the canyon, but very little, especially in the higher elevations of the canyon. Now let's take a look at sedimentary rocks. Now when we talk about sedimentary rocks, we're talking about rocks that were deposited by running water or wind. And it's important to understand that these are very identifiable. What many people don't understand, and what becomes a very important issue when we look at the canyon and the question of the flood of Noah, are what are the different kinds of sedimentary rocks. Now basically there's two fundamental types. One is called a clastic sedimentary rocks. What that means is that material was carried and deposited by wind or usually running water. Wind is really kind of rare. Put down in layers and turned into rock. Now an example of that you can see here on the table, because we have shale. Shale is mud turned into rock. And a lot of times when we split open a piece of shale like this, we see little fossils inside, which tells us that this was in an ocean environment. And by the way, if you put this under heat and pressure, it would turn into slate. But that's mud turned into rock. Sandstone is sand turned into rock. And isn't that beautiful? Those are called picture rocks from Utah. Different colors of sand deposited at different times, and sometimes it had a lot of iron in it, so you get these red colors. Sometimes it had mostly quartz. Actually, in Zion National Park, which we'll take a tour of here before long, you're going to see that most of the sandstone is quartz sandstone, so it's very white in a lot of places. But every now and then iron has impregnated the material and you end up with something of this type. Gravel can be turned into rock. You can get actual pieces of gravel cemented together to make rock, which is called conglomerate, or sometimes the name breccia is used if the pieces of rock are very angular. Now this is one kind of rock, a clastic rock. And this is the kind of rock that would be produced by a flood. When people have a flood, what are they doing? They're cleaning mud out of their house. They're shoveling sand out of the living room or gravel. So these are flood deposits. The trouble is that sandstone could also be a wind-carried deposit. So how would you tell the difference? Well, there are several ways, and we'll look at some of those while we're in the field. But one thing that you find out is that the sand grains tell you a story. If it's an air-deposited sandstone, then the sand bangs into each other like that. You get a lot of collisions of the sand particles. And so the sand is frosted. Now we'll take you up to Tower Hill here in Michigan shortly. And the grains of the sand in Tower Hill, which is a sand dune, are frosted by having been banged into each other. The angle of the dune is not very steep because when you get wind depositing sand, it slides because air doesn't hold it up very well. Now, on the other hand, if a sandstone was deposited underwater, then the sand grains don't bang into each other very much, so they don't get frosted. So the sand will actually be quartz, and you can see that it doesn't have scratches and grooves and frosting in it to any great extent. Not only that, but when you see a deposit of a sandstone, it will be steeper because the water has a buoyant effect and holds it up. So when we take a walk down the Grand Canyon, you're going to see a coconino sandstone. The question is this a water deposit or is it a wind deposit? These sandstones here, like this beautiful picture rock, are pretty much frosted materials, and they have obviously moved around a great deal. We're pretty sure that most of what we see in this is a wind-deposited area. Now that's a clastic rock, but we also have some chemical precipitates. Now what we have here is a chemically precipitated rock, like this geode. Isn't that beautiful? This one came from southern Indiana. Actually, my mother-in-law found it out on a farm near her house. But when we take a little tour of my rock garden here, I'm going to show you a lot of these because they're all over southern Indiana. This one came from Oregon, a little bit different. Now, sometimes these can be volcanically deposited, but usually ones like this are sedimentary in nature. Here's another sedimentary rock. This is a limestone that again is a chemical precipitate. Now you say, well, what do you mean by a chemical precipitate? I mean that you had conditions where you had a water environment and it was very quiet and very still, and crystals grew in that environment. You've all seen rock candy. You've seen maple syrup left on a cellar shelf too long. Maybe jelly that was forgotten on an ancient cellar shelf. And what grows inside there are huge sugar crystals. Well, that's essentially what happens in this geode. Crystals grow over a long period of time, and I don't mean astronomically long necessarily, but under quiet conditions, certainly not the kind of thing that you have in a flood. And many times when you find a limestone, a chemically precipitated rock, you find something else that's sort of an indicator. And look at this one. Now, this is a limestone. You put acid on this, it fizzes like mad. It's calcium carbonate. And do you recognize this? Yeah, it's a piece of coral, isn't it? Well, this was the same rock that this was found in. This came from southern Indiana. And I had an awful time chiseling it out of bedrock. So there were corals at one time growing in southern Indiana? Yeah. Yeah, as a matter of fact, there are corals in the Grand Canyon. So you know that because there are corals and because there are chemically precipitated rocks and because you have an environment that indicates a sedimentary nature, it's not a volcanic nature, it's not a clastic nature, it's a very special kind of environment. So when we look at rocks, they tell us the history of the area and tell us something about the nature under which they were deposited. Now, was the Grand Canyon produced by the flood of Noah? Now, the first point that needs to be made here is that the Bible simply tells us about a flood. It doesn't tell us whether the flood was instrumental in producing things like the Grand Canyon. What kind of rocks are in the Grand Canyon? Mostly chemically precipitated rocks, limestones. Now, there are shales like the one I showed you. As a matter of fact, you remember the canyon, and you'll see this as we travel in the canyon, that sometimes it's vertical and sometimes it's like this. Well, the vertical rocks are the limestones. Very hard, very tough to break. The only way they usually get broken is to get undercut and then fall off. The areas that are lower, easier, less dramatic, those are shales usually, and sometimes sandstones. They are clastic rocks. So somebody will say, well, yeah, but at Mount St. Helens, you have a situation where you have a canyon produced in a very, very short period of time. And as you look at these slides of Mount St. Helens, what you see is that this is clearly a volcanic area. The question is, what kind of rocks are these and how tough are these rocks? Let's do a little experiment. All right, so we're going to do a little experiment here. I have a piece of rock from Mount St. Helens, and I have a piece of rock from the red wall limestone from the Grand Canyon. You say, what do you mean a red wall limestone? That ain't red. Yeah, the red wall is not really red. The red wall is stained from material above it. And when we walk down the canyon, we'll make that point to you. This is the actual stuff. And the question is, are we valid in comparing the erosion rates on Mount St. Helens, where you've got a canyon that maybe is 1,500 feet deep that's been carved since 1980, short time, with the Grand Canyon, where you have a very deep canyon? Could the flood of Noah have produced the Grand Canyon? Now, we've already indicated one problem. One problem is that the rocks that are in the canyon are not flood rocks. I mean, people are not shoveling limestone out of their living rooms. They're shoveling sand and gravel and mud out of their living rooms when they have a flood. That's the first problem. But the second problem is the erosion rate. All right, to be a good boy here, I'll put on the glasses because you're not supposed to do things like this without eye protection, which is a very good point. And I've got a sledgehammer, and I have a piece of Mount St. Helens rock. Let's give it a little whack here and see what happens. Well, that's interesting. Let's try the red wall limestone. My goodness, it's pretty hard. Didn't even scratch it. There, I finally got a piece off. Is this stuff going to erode at the same rate as the St. Helens material? You know, that's like comparing steel with butter. The erosion rates in the Grand Canyon are going to be nothing like that. And you got to remember here, I'm using steel on this thing. And I really didn't do much to it. I just knocked one little chip off of it. Now, don't misunderstand what I'm saying here. I'm not saying the flood didn't happen, not at all. I'm just saying that attempting to use Mount St. Helens to explain the Grand Canyon is a totally incorrect concept of what is involved in the rocks, both how they were produced and how they weathered. Now, we thought one thing that might be kind of interesting to you is to just take a little tour of my rock garden. There's no charge for this, but it's just sort of an interesting demonstration of some of the things that we're talking about. When my wife and I do lectureships, we don't buy souvenirs, can't afford it, but what we do is pick up rocks. And I have my rock garden arranged in terms of some of the rocks that we have found, and I just want you to see the variety here. Now, down on this end, we have geodes. Most of these geodes, like this one, which we'll show you more about, these are from southern Indiana, where I grew up. And they are chemically precipitated rocks. What happens in these things is that you have some material in the center, and then quartz is deposited around it, and you end up with this concretion, and then the material in the center erodes away or dissolves away. So sometimes you'll find a different mineral inside here. And sometimes you find very valuable stuff, different kinds of quartz minerals. Now, some of these are from the western United States, like this one, and they're perhaps a little bit different in form. Now, as you move across here, what you find are sedimentary rocks in this next section, like this. Now, actually, that came from deep down in a sand deposit in the Bahamas, so it really doesn't qualify with the rest of these. But this one came from Bloomington, Indiana. They're a different species of coral. This is a brain coral, but nevertheless, this is from Bloomington, Indiana. This came from Canada, Lake Nipissing. And this piece also came from southern Indiana near Indianapolis. Now, these other rocks, limestones that contain fossils, and notice that they're different in nature. Some of them have different kinds of fossils. This one is from Kentucky. This one's again from the Bloomington area. This one came from Illinois. Here's another piece of coral. That piece came from Illinois. This is from Kentucky again. And look at this. This has got mud cracks in it. These are cracks that are preserved in this thick shale. And it tells us that at one time that must have been an evaporating type of deposit. Now, the sedimentary rocks end with this layer here, which is from the Grand Canyon. And as you start moving into the next section, you get into volcanic rocks. And we've talked about lava, extruded rocks. This one came from Idaho from craters of the moon. This came from Hawaii, as did a couple of these. And they're very clearly volcanic in nature. This one came from Spokane, Washington. Picked that up when we were visiting the World's Fair there, doing an exhibit there. So as you can see, it looks very much like part of a lava flow. This came from Yellowstone National Park. You say, how do you remember those things? Well, I'm a geologist and I recognize the environment in which they were formed. Some of them came from mineral tailings near mines, and some of them are pegmatitic rocks. What that means is that they are places where hot water came up through cracks in volcanic rocks and carried the minerals with them. And so you see also some granitic material. Some of this, like this Saginaw granite, look here, we see an actual fault in the rock. The crack runs up through this. This vein must have been connected at this at one time, and you can see the drag as the rock broke. Here's other minerals from Saginaw granite as well. As you move further over here, we start seeing rocks that are metamorphic in nature, showing the effects of compression. This rock right here is a schist. We mentioned that in our discussions. Sometimes you'll see the Vishnu schist and other rocks like that. What's happened here is, and I think I'll set it, maybe you can see the shininess of it there, but you see mica in the rock. The pressure came from this direction and the rock is layered out. And so you have a metamorphic rock, a changed rock. Here's another example of an extruded rock. That's some obsidian that is, again, from Yellowstone National Park. And here is another example of metamorphic rocks with the layering. The rest of these rocks that you see around the edge here are mostly Michigan field stone. And what does that mean? Well, it means that these rocks were carried in here by the glaciers. And what you see is every kind of rock imaginable. There are volcanic rocks, there are sedimentary rocks, there are lavas, there are all kinds of materials. As a matter of fact, one of the interesting things is that my students actually have found pieces of something called a jasper conglomerate, which is the only place we know of where that is existent is in Bruce Mines, Ontario. And Bruce Mines, Ontario is on a line that we think the glaciers traveled into this area. So reading rocks tells you the history of the area. And kids have a good time with this. We have a lot of fun with this. I had a student that actually found a small diamond when we were digging in a gravel pit once on a field trip. In glacial till? What does that mean? It means that somewhere north of here, there must be a Klondike. There must be a place where conditions were ripe for the production of diamonds. Find it, you can become a billionaire. But the important thing to understand is that this tells us about the history of the area. And we have tried to say throughout our discussions that science and faith support each other. They reinforce each other. They exist in a symbiotic relationship. Being able to read the rocks and to understand what the rocks has to tell us about a history of an area is a marvelous way of seeing how God has functioned in the history of the earth, His wisdom, His planning, and how He has marvelously prepared the earth for man.